Right. Thank you again, Sarah and Mattei. I would like to introduce Cristina Silvano, who is from Politecnico di Milano. She, along with Axel Hubel, are the chairs of the PASC23 Papers Program Committee, and Cristina will introduce our next presenter.
Thank you very much, Mike. Let me announce now the PASC23 Best Paper Award. The award goes to the paper on FourCastNet, Accelerating Global High-Resolution Weather Forecasting Using Adaptive Fourier Neural Network Operation. And let me introduce our presenter, Thorsten Kurth from NVIDIA. Thank you for coming. Let me say that Thorsten is working on accelerating HPC application for GPUs at NVIDIA, and he was the 2018 awardee for the Gordon Bell Prize for the first deep learning application reaching 1 exaOP peak performance. And he was also the Gordon Bell Prize Special Award for HPC-based COVID-19 in 2020. So welcome to PASC, and the floor is yours.
Thank you very much. Yeah. So, thank you very much. We feel very honored for this award, and I'm honored to be here and can present this work to you. And if you do a string difference on the title, on the intro slide and this slide, you will see that I dropped one word, which is adaptive here. And this is because the research on this project is an ongoing work. And I'm also going to present you some newer results in this talk, which is probably very interesting to a broader audience like this. So this is the team behind this, and I also want to thank everybody on that slide as well, since without these people, this effort wouldn't have been possible. And this is like really a multi-institution effort. So we have NVIDIA people, LBL, Caltech, so it's across different academic institutions and industry. So I will give a very brief outline. I will talk about what data-driven weather prediction is, because this is what FourCastNet actually does, and compared to numerical weather prediction, and then dive right into the neural network architecture we designed and trained, and some results there. However, I also want to take you further. So when you go from weather prediction to more longer-term rollouts, for example, relevant to climate science or subseason to season science. And for that, I need to introduce a new network architecture which stabilizes these things and deals with some of the inefficiencies of the one I'm presenting you next. And then I will give a short outlook of what's going to be next. So, traditional NWP, or numerical weather prediction, is, you can summarize it in one word, although it's very tricky to do. So it's basically solving equations of motion of incompressible fluids on rotating sphere, but then you add lots of tricks, and that is where the caveats come in. So you have a lot of numerical models and heuristics developed over decades, right? So the weather prediction today is super good because there's a lot of knowledge of a lot of PhD students, researchers went into these models and give you basically what you see today. So very good accuracy. And the issue is like what you're usually interested in is you start with some initial condition, then you evolve it, right, using these supercomputers, and you're not only interested in one initial condition, basically you perturb the initial condition as well, and you create basically this bundle of trajectories so that you have a forecast uncertainty, and this is very important. However, producing these long prediction rollouts and large ensembles is super expensive. And why do we need this? Why do we need these large ensembles? So this is a small cartoon of why this is important. You need to capture them you need these large ensembles to capture low likelihood, high impact extreme events, right? Or black swan events, they're sometimes called. For example, in winter in California in December 23, we had these multiple atmospheric rivers, which are like large-scale structures, which transport a lot of moisture, basically dropping all in on California at the same time and causing heavy flooding and other disturbances. And the issue is this: when you look at the probability distribution, like shown here, So this is for temperature. I don't have one for the atmospheric rivers, but the idea is the same, right? Usually, when you quote, like, for example, climate change effects, you quote mean, maybe the mode of the distribution, but these long tails are what counts. Because everything in this long exponentially suppressed tail is what costs money, right? It costs people lives, it costs a lot of money and property damage. So we are interested in actually this tail. So how can we get there? How can we get like realistic estimates of how disastrous certain weather conditions will be? So for that we need fast sampling, and how do you get this? And one idea would be data-driven weather predictions. So they're pretty similar to, like, let's say, series predictions of like images in, let's say, movies to fill in broken frames, or like in video games. If you stream video games, you basically might want to reduce the frame rate, or like make up a higher frame rate by just interpolating images cleverly using AI. And instead of images, of course, you have like physical fields. So this could be like temperatures, wind pressures, and similar things, similar variables. So the important aspect here is that this can be stood up by small teams also. So you don't need a lot of domain experts around you to basically do this kind of things. You just need some DL knowledge, have access to the data, that is very important, and then you can go on. Of course, I don't recommend not including any domain scientists in your work, but technically you can get started without it, and then communicate with this expert and improve on your research. So, and we've seen this recently where there's a lot of great solutions around. For example, there's Pango Weather, there's GraphCast by DeepMind, and the newest kid on the block is Foxy. So this was actually released, I think, 2 days ago or something. So I haven't read into this. It's basically a wavelet transformer architecture. This is a graph neural network, and this is a 3D transformer. And they're already showing very good results with relatively small teams of just maybe 20 people involved. So, the other, of course, good news about this is that producing these long rollouts is actually pretty cheap. Okay, so how does it work? Data-driven weather prediction. So you have a state at time t. It can be like a multi-dimensional state. So like 200 different observables, for example, you're interested in on a lat-long grid or some other geometry or some other grid. You feed it to a deep neural network, and this produces a prediction at time t plus delta t. So the delta t should be tuned to like the smallest timescales you want to make predictions for. And then if you want to get longer predictions, you just feed this state back into the deep neural network, this step is called autoregression, to get a prediction at t plus 2 times delta t, and then you just repeat the process till you have a long enough rollout you're interested in. And of course, you can, at every step, you can technically compute the difference, or some loss compared to the ground truth, compute some loss and train your weights. So that is basically how it works. So you need, of course, a lot of high-quality ground truth data. Getting that can be a bit tricky, especially in very high resolutions. You might need to pay for it. But other than that, it is more or less straightforward. So our architecture we proposed first, and that was mainly part of the main topic of the PASC paper, is the adaptive Fourier neural operator, and it basically merges the vision transformer architectures and Fourier neural operators. I don't want to talk about what Fourier neural operators can do. They basically learn mapping functions to functions, and they can technically be resolution invariant if you structure them correctly. And they have been very powerful for like physics-based problems. So how does this architecture work? So first of all, you have this input grid, and then you tokenize it. That is what most transformers do. So basically, you patch it up. You chop up the image into patches, and then at every patch, you basically embed the features of every patch into like a tower of features. You basically attach to the point of this reduced resolution grid. So it's not a coarse graining step because you preserve the features in this embedding. You need some positional encoding, right? Because the transformers can otherwise like freely mix up these patches and doesn't know where they came from. So you need give it some idea of where the patches came from. That is important. And then we have like these transformer blocks, and the good news is they are very like homogeneous. It's always the same work. There's no downsampling included or anything. And they consist of 2 steps. So first is we have these long-range features we want to extract, and for that we mix the patches using 2D FFTs, which makes it very efficient. And then within the patch, we just use dense MLPs to mix basically the features inside the patches themselves. We do some normalization, but in the end, we transform this back to the basically the input grid resolution. So that's important. This paper was published here. It's an archive. for PASC and MS. So this we also have the model itself was published by ACM WF Lab and is available on NVIDIA Modulus. So ACM WF Lab is interesting because they started this effort quite recently. So where you can basically get the models, the source code of the models, and just basically pip install it and try it out for yourself. So I think this is a great effort, and it's good if more community-driven models go in that repository and people share their work. So training this model can be quite expensive since it has a lot of parameters. So what we need to do is to parallelize it. And we go beyond the traditional data parallelism, what you usually find in large-scale deep learning training. And what we do was rather like applying like 101 HPC textbook parallelization. So one is domain parallelism. Since we have a large domain, we can just chop up the domain, the spatial domain, which means we need to use distributed 2D FFT. But how you do this, it's totally clear. You use all-to-all in some kind of pencil decomposition, and you're happy. Feature parallelism is just by chopping up these huge, I said we have this tower of features we need to deal with. We multiply that by large matrices. So you can just like split up the matrices in like how you basically do a distributed matrix multiplication. It's pretty straightforward. And this is, for example, also what Megatron does. Or these large language models. This is one of the main aspects of how they parallelize the models. Of course, they have much more fancy than that right now, but generally this is what they do. And the communication pattern is more like all reduce, all gather dominated. So it's different. So depending on what kind of communication primitives you can scale better, you will get better or worse performance depending what you do. And then you can mix this all with data parallelism. And one word about the implementation. So you don't need more or less any external packages for that, for doing this kind of model parallelism, because PyTorch can do everything out of the box. I don't know how many people know about that. So you can implement your own backward functions, the forward-backward functions, explicitly using Torch Autograd. You can also modify how distributed data parallel works. So, for example, if you have shared weights, you might not want to reduce them across. You might want to reduce them across all the nodes, but you might not want to reduce like sharded weights across certain groups of communicators. And that you can all nicely implement using communication hooks. This was added like a year ago, like 1.5 years ago. It is super useful for these kind of tasks. So you can basically specify like the whole flow of how you like implement it in a very custom fashion. So for data loading, we use NVIDIA DALI framework with external sources. NVIDIA DALI is a very high performance data loading framework. It mostly focuses on images and audio data, so more like industry relevant. But it has a certain plugin you can use to hook in any PyTorch or like Python functions you want, and that is what we use for this. And very important, you should use CUDA graphs. So CUDA graphs basically record a sequence of kernel calls and then just replay them over and over again. And this is super important if you scale out your models because it reduces jitter tremendously. So PyTorch has this in eager execution mode. So if you do not use CUDA graphs, it will the CPU will always be trying to figure out what kernels to launch next. And this interference gives you at large scale gives you a lot of jitter, right? Because some GPU might not launching its nickel collective because it gets stalled on some CPU work. So this is super important, and of course mixed precision to get trained faster. So we have FP16, recently BF16. And we have a lot of other optimizations, mostly like compiling kernels and things. It's too much to talk about this right now. So this is like the strong scaling. So this is just as part of the scaling up to more than one DGX A100 node. And it should just demonstrate the following. So this is just the execution time of a single transformer block. And these are the workhorses of that. So it's basically 99% of the work of this network. And it should just illustrate that you cannot get along with just one type of parallelism here, right? So you have this feature parallelism, the blue line, and you see it scales okay in this strong scaling plot. But what you really want is domain decomposition. But if you scale beyond 8 GPU, that is when you leave your NVLink island, you're basically getting a performance penalty because your all-to-all collectives do not perform as well anymore, whereas the all-reduced collectives still do. So the trick is just to use hybrid parallelization and basically combine both communication types in your network, and then you have a rather good scaling. And of course, you want to mix in data parallelism as well. So we ran this on 3 different systems: Joules, Booster, Perlmutter, Selene. They're slightly different by number of GPUs per node or the interconnect they're using. And as you can see, they're all like it's scaling pretty nicely up to like a couple hundred petaflops. And here in the Selene plot, I want to show you how this model parallelism kicks in. So when you look at the red line, that is when one GPU is just running one model. It's just the whole model. And then when you split it up across 2 GPUs, you basically jump onto the blue line, right? Like the lowest point on the blue line. And then if you split it up again, you jump up. So of course, you don't get a speed up of exactly 2 because you add some critical communication, like some communication into your critical path. But on the upside is you do not increase the batch size. So you don't need to retune any hyperparameters, right? You can just go along like basically across these trajectories and without any tuning of your parameters. So that's kind of nice. So we trained this on 25 kilometer data. This is the ERA 5 reanalysis data set. And the training time was about 70 minutes on 3K GPU. And actually, the functional performance of the model, like the skill was pretty good. The inference time is then 70 seconds for a 100-member ensemble on a single Perlmutter node, which is 4A100. So that is pretty nice. So we can produce very large ensembles very quickly. So here's some skill plots. So this is IFS, this is the yellow line. This is basically the gold standard we're comparing against with some error bars. And then we have a 20 variable. FourCastNet, we extended to 26 variables. So more recently, we even have 70 and 200. But you get the idea that you can just incorporate new features and it will just improve the skill. So this is very interesting because you do not need any domain knowledge to incorporate these features. You just make your network a bit wider and just get these data points and you can increase the skill. So this is quite impressive. It also has impressive skill on extreme forecasting extremes. For example, these are like some notoriously difficult to project hurricanes like Florence, Isaac, and Selene. As you can see, like in the initial conditions, looks quite harmless. There might be one hurricane, but then it generates like these 3 ones, and FourCastNet actually can predict all of them. And those were like pretty tough. So generally, the network has the capability to capture these extreme events, which is very interesting and important. So now, switching the scopes the last couple of minutes, we want to extend this to climate science, right? Because this is a grand challenge. Everybody is affected by this, and it's good if we can maybe help with AI driving innovation here and trying to solve one of the biggest problems. So this plot I stole from a paper. The idea is that there's a tremendous growth in compute and storage requirements if you do it the naive way, right? So you cannot do it unless climate. So once we get here, it's decades in the future, right? So this is very hard, and we want to basically try to skip some of this in time, and hope that AI can achieve this actually. So one possibility is, for example, consider tethering. A traditional climate simulation trajectory looks like that. You have an initial condition, let it evolve, get a different one, and so on and so on. And you have all these different checkpoints you basically want to store, because you want to also have high resolution in time. But this is super costly. It can be petabytes, it can be zettabytes of data. This is a lot. So you can either compress the data, or you can maybe drop checkpoints in between and try to interpolate in between checkpoints using some ensemble forecasting using AI-trained models. So this is one idea of how to fight that. And the more you can roll out, the more stable rollout time you have, the more checkpoints you can technically, you don't need. So there's one thing of FNO, and this is of polar instabilities, and this is why I want to show you this plot, because not everything is golden here. So there's the topology AFNO assumes is S1 by S1, so it's a torus. But the Earth is not a torus, as you know, right? It's a sphere. So what you can see here in the water vapor, it will basically crash the simulation at some point. So you have these artifacts forming and totally falling apart. This is not good, right? And this is basically the autoregressive feedback loop amplifies small errors over time, which will totally kill the simulation or the emulation. So what we need to do is we need to go and formulate this model on the sphere. And for that, we have implemented a small library called Torch Harmonics. You can check it out. It's open source on GitHub now. It has efficient calls to SHTs, so spherical harmonics transforms in forward and backward paths. So you can fully auto-diff through it. You can use distributed computation with it. It uses some kind of pencil decomposition similar to 2D distributed FFTs. And with that, we implement a new topology, which we call spherical Fourier neural operator, so SFNO, and it's fully SO3 equivariant, right? So it's fully, it respects the symmetry of the sphere fully, end to end. And it's one part is to replace the Fourier transforms with the spherical harmonic transforms, but you need to go further. So you need to really go through every aspect of your model and see what is not SO3 equivariant and replace with something else, which is. So for example, layer normalizations can be very dangerous because they have element-wise affine transformations, so you attach a different transformation on every grid point, which is not a good idea. And also when you do MLPs, you need to be careful that they are like, they have to be pointwise, for example, either in spherical harmonic space or in real space. So looking at these instabilities again, on the left side you find the AFNO, which crashes, and on the right-hand side you see it just going on with the new SFNO model. One thing I want to point out is this, this small artifact you see here forming. This is some kind of like Gibbs oscillation phenomenon. This comes from the fact that our model has one big skip. So a big skip means you take the input and directly feed it to the output and combine the features. So this is because the high frequency modes, the noise in that modes is not suppressed, and it will amplify over time in this autoregressive rollout. So we understand very well where this comes from, and we could eliminate it in a more recent iteration. It's pretty straightforward. It's signal processing on a sphere, basically. The thing is, I didn't have time to create like a new animation for that. So I apologize. I just wanted to point that out to you. But generally, it's very stable and very for very long rollouts. And this is also shown here. So this is the ground truth. This is the animation for the SFNO prediction. And of course, at some point, the trajectories will diverge, right? So the states will look different. This is why I just moved this other one, the ground truth, to the side. But the important part is that you still generate realistic weather patterns. So now you will need to do some statistic analysis whether you capture the right distributions of events. So that is the next step. So we haven't gone that far, but as you can see, it rolls out over a year without any breakdown. So this skill-wise, we compare to IFS again. These are 4 plots. I don't want to go much into detail here. So the yellow line is basically the IFS prediction. The blue line is the IFS prediction. Orange line is the SFNO one. So you can see we even beat it, and the 10-meter eastward wind and some other channels. We are pretty much on top. A bit tricky is this geopotential at 500 hectopascal. I actually have no clue why. It looks very smooth and harmless, but it's a bit tricky to capture. But we are working on improving the skill as well here. So this is for 100-hour rollout, so more like medium forecast. Okay, so I want to also point out there's a paper on this accepted for publication at ACM, Spherical Neural Operators, Learning Stable Dynamics on the Sphere. The archive link is there. And also, please, for more details about neural operators in general, check out Anima and Kurma's talk. So she gave a remote talk yesterday on this specific one, but also more general applications of these kind of neural networks. So the summary: we developed a high-skilled fast weather prediction model with stable long rollouts. In that process, we open sourced this small library for differential spherical harmonics transform. Hopefully, it will be useful to somebody. If you find some, like, for example, it supports different input grids, but not all grids. So if you want something implemented there, just file an issue. We want to attack sub-seasonal to seasonal predictions and climate science challenges with this new model, and also increase spatial-temporal resolutions, which is a big challenge. And we are also making it public, so the source code as well as the weights. It will be probably on the NVIDIA Modulus page, but yeah, so that is a work in progress and will happen in the next few weeks, I think. And with that, I want to close. Thank you very much. And I take questions.
Thank you very much, Thorsten, for this very nice talk. I see a question. I can move over there.
Thank you very much for the very nice talk. You are showing more continuous variable. Could you comment? Are you also able to generate like precipitation fields?
There is a collaboration with LBL going on where they try precipitation. This is much more difficult because also the data is distributed like there's mostly like 0 and then it has a long tail, right? So we are using some basically some attachment to the original model, which deals with these precipitation issues, and it also uses, I think, some generative approaches to get there. So this model cannot do it, and it also has, so there are other variables which have like which are not as continuous. For example, when you look at relative humidity, it has some very sharp gradients. So we can capture those, but it's a bigger challenge, yes.
And so just follow up on the data you generate. Are you able to generate 3D fields, which would be also very interesting for scientific study?
Generally, yes. When we try to include 3D features, the computational cost goes up tremendously, but for the variables we predict, it didn't make a big difference. So, but we are looking to include like basically more features on different altitudes and try to include 3D effects. I think for presentation is maybe more relevant than for some of these.
So
Thank you for your talk. I wanted to ask also a similar question. Have you also tried with trace gas concentration? Do you have any research in that field?
So,
like using the same model for trace gas concentration forecasting?
So like,
or always you have the same features like temperature, wind, and there's no other variables to try?
So we are including like, so in the more recent models we're including 73 variables. We will have a table of that. So like we start initially with just wind and temperature and like, so we included like water vapor and like relative humidity is one of the later ones. And then, for example, when you look at the FourCastNet paper, they have a list and we basically include all of these plus a few more. And also we try now to go for, these are more challenging, like these sea surface temperatures and land surface temperatures. Those are more challenging because they're a bit more discontinuous and you need to mask. So we are working on that too. Like including new features is generally unproblematic unless they come with very like discontinuous behavior or missing data. So that is the problem we need to sort out, because the issue is with this architecture, it's not an issue, it's like a challenge, let's say. When you have missing data, the Fourier transforms or the spherical Monte transforms correlate the data with every point. You cannot just have no data there. So you need to have a way of dealing with this and not like polluting your Fourier transform with that. So that is a bit of a challenge and we need to figure out how to do that. And we likely want to stay away from non-uniform grids, so. But that would be an option to do that as well. So.
Yeah, thank you for your presentation. I would actually like to challenge what you are presenting. And my challenge is as follows. When you take the Fourier neural operators and you apply them to the Kuramoto-Shivasinski, you don't go further than what any other neural network method does. I have tried it, and I would welcome to collaborate with you that you tried, and you tell me what you get. I think I tried open source software, so if the system is chaotic, it doesn't work. If you take a Reynolds number, flow around a Reynolds number, I have never seen a Fourier neural operator do a Reynolds number of 1,000. If you have that, I would like to see it. So the challenge is, yes, you can predict. I think all neural networks can predict, but also, as you were showing, at some point you predict and then you fail to predict. So is there any remedy for that? Or is there any way to know when you're going to fail? What about trying to predict weather for which you don't have the results? What are the metrics that you are predicting or not predicting? And so these are the two things. I would welcome a comparison of Fourier neural operators with other techniques, and I would like to see on simple problems where we know the answer, and also how do you know that what you're predicting is correct? Thank you.
Yes, so I take this more as a general statement than a question. So you're right, it's hard to test. It's also hard to agree on a performance metric at all, right? So you see in literature, you see some quote the RMS error, some quote the correlation coefficient, some quote like CPRS and these kind of things. So generally I agree, it's hard to estimate like a priori where this thing breaks down if you don't have data. So it's more or less, I think, of establishing a trust in the model over a certain time range, back tested on historical data, and then assume that it will work on future data. But I agree. So what I think want to work on is more like on a statistical analysis of, does it predict the right statistics of certain observables in the future? And that is ongoing, yes.
Thank you.
Yeah.
Okay, thank you very much. I think we don't have enough, maybe only one more question.
Yeah,
please.
Thank you very much. So could you come back to your scaling curve, so strong scaling curve, please?
Yeah, this one?
No.
This one?
Yeah, that one. So do you have the parallel efficiency? So if I'm correct, there is almost factor of 2 between the ideal. So it means that it looks like it's below 50% of efficiency here.
So this is strong scaling, right? This is so the scaling is basically for the like totally is about like for the purple line is like 1.5. But if you do performance modeling, that is the best as you can get. And some of the issues are that if you just if you do not write your own like fully integrated kernel, which does, for example, matrix multiplication and hides some of the communication, this is what you end up with. So the issue is we want to make it composable, we want to attack it from a PyTorch level, but you can of course go in and fuse some of these kernels together into bigger kernels where you can more efficiently mitigate these issues. So I agree that is the case, but generally this is definitely good enough for what we are trying to do here. So like having like ideal scaling is, I think, for this kind of application, especially when you have like distributed Fourier transforms, becomes challenging.
Yeah, but back to the previous talk with energy savings and trying to use resources as much as we can.
Yeah.
So then what would be then the good production point here, so in your opinion?
So one thing would be here, so this is, so one thing would be, first of all, with newer architectures, for example, like with the GH200 system, where you have multi-node NVLink now, you can scale the red line out much further, and it's much easier, for example, to provide an efficient distributed FFT than just like a mixture of FFT plus matrix multiplication plus FFT layers. So from that perspective, I think the scaling can be improved beyond that. So this was like one of the earlier scaling plots we have, efficiency-wise, it's also a matter of can you train it at all, right? So part of why you want to parallelize it is that if your number of weights are if the total memory footprint is bigger than your single GPU, you are lost, and that is the case here. So so the estimates are if you go to 10 square kilometers, you need to run at least on 64 GPUs because otherwise it will not fit even in memory.
I see. Thanks.
Okay, so I'd like to thank you again, Thorsten,
for
your very nice talk.